Now we already solved one system of equations using Gaussian elimination, but we did it before. We looked at how the recipe on a step-by-step approach on how to do it. So, how do we solve a system using Gaussian elimination? Well, first thing you do is write the augmented matrix for the system, and then we use row operations to obtain an equivalent matrix that is in row echelon form, which is like this. And here is the order in which we do it. Get a 1 in row 1, column 1. Rows go to left to the right and columns are going up and down. So turn that top left entry into a 1 somehow using one of the 3 row operations. Then use that 1 to get all zeros below it. Okay? 1, 0, 0. And then we come down this diagonal, we go down to row number 2 and make sure we can turn him into a 1 and get all zeros below him. And then notice it just says continue because here's an example. We go down to row 3 and we turn this into a 1, and there could be, if this had more 4, 5, 6, 10 rows, we would use this one to get zeros below. And then we would move down to this one, get zeros below, and then down to this one, and so on. You just repeat that over and over until you've taken care of all of the rows. And then once you're done, you can write the new system of equations from this matrix and solve it using back substitution. And for this one, since this is just a 3-row matrix, it means there were 3 equations, x, y, z. You know that for example, z is whatever number is right there. So once you're done, you automatically know what z is just by looking here at this number. And then knowing that, you plug it into this and you can figure out what y is, and then you go backwards. When we look at row number 1, we know what y is and we know what z is, and then we can figure out what x is. All right, let's do one more example of Gaussian elimination. And this will be a little bit different. Notice that if you just jump into writing the matrix, it's possible you would make a mistake. We need to have everything lined up perfectly. The x's, the y's, the z's, the equal signs, and then the numbers to the right of the equal sign. So I'm going to rewrite these in the correct form. So it looks like it would be x plus 2y. Then what? Not z, but minus z. I have to subtract z from both sides. Minus z equals -1. So all I did was subtract z from both sides. Well, what do I want to do here? Well, there's multiple things. There's 2 ways you could do this. Since let's see. X is on the left, so we either need to subtract y from both sides and add z to both sides, leaving 4 by itself. Or, since we have y and z over here, I could subtract x to get it on this side and then subtract 4 to get it on that side. And it doesn't matter which way you do it. I'm just going to keep the x where it is. Subtract a y, so minus y. Add a z, so plus z, equals 4. Okay, so we have x minus y plus z equals 4. That looks right. And the bottom one, the bottom one is the correct form, the general form, where you have an ax plus by plus cz equals d, so to speak. So x plus y minus 3z equals -2. So now I'm going to make the matrix from this one, now that it's all lined up correctly. So I'll get a 1, 2, -1, -1. 1, 2, -1, -1 for row number 1. For row number 2, I get a 1, -1, 1, 4. 1, -1, 1, 4. And then 1, 1, -3, -2. 1, 1, -3, -2. So make sure you create this matrix incorrectly. Excuse me. Most of my examples come out with nice integer whole number type solutions for x, y, and z. But if you mess a sign up, you will not get that correct answer, and it could come out to be very ugly fractions for all x, y, and z, and just take you more time to get it done. Nothing wrong with fractions, but most of the examples, I think, have a nice whole number or integers for x, y, and z. So let me double check. 1, 1, negative 3, negative 2. Second row, 1, negative 1, 1, 4. 1, 2, negative 1, negative 1. Looks good. All right, well, just like the previous example, I'm making this too easy. We already have a 1. That's the very first thing you do. You need to get a 1 in that position. If that number happened to be a 2 instead of a 1, there are multiple ways you could turn it into a 1. If it were a 2, you could just trade 2 rows. Switched row 1 with either row 2 or row 3. Or if it were a 2 in that box, you could subtract row 2 from it, or row 3 from it, and it would give you a 1. But we started off with that 1, so now let's use that 1 to get zeros below it. This will be really easy. All I have to do is subtract row 1 from row 2, and subtract row 1 from row 3 to get zeros below it. So I'm going to say row 2 minus row 1, and row 3 minus row 1. If you didn't notice, I like to write the row that's changing, row 2 minus row 1, I like to write it on row 2. And row 3 minus row 1, we're changing row 3, I like to write it right there instead of up here. It wouldn't be wrong to do, well, it makes it much more clear if you put this on the row that you're changing. Row 2 is changing here, row 3 is changing here. All right, so row number 1 is not going to change. 1, 2, negative 1, negative 1. And as you can see, I'm kind of going downhill here just to avoid this system up here. Row number 2 minus row 1. So 1 minus 1 gives me a 0. That was what we wanted. What's negative 1 minus 2? Negative 3. What is 1 minus negative 1? It's not 1 minus 1, it's 1 minus negative 1, which is 1 plus 1 for 2. 4 minus negative 1 is 5. Bottom row, we need to do row 3 minus row 1 in order to give us a 0 here. 1 minus 1 is a 0. 1 minus 2 is a negative 1. Negative 3 minus negative 1, that's negative 3 plus 1. Negative 3 plus 1 is negative 2. And negative 2 minus negative 1 is negative 2 plus 1, which gives us negative 1. Okay, so great. We got this 1, we got zeros below it. Now we come down here, and I need to turn that into a 1. Well, one way to do it would be divide this whole row by negative 3. And then we would get fractions like 1, negative 2 over 3, negative 5 over 3. How about if we just trade these two bottom rows? That would give me a negative 1 there. Oh, I got a good idea. I'm not going to write a whole new matrix for this, but I'm going to do this row operation. Negative 1 times row 3, because that'll change the sign of all of these. Right? It's multiplying by negative 1. So it becomes a plus 1, plus 2, and a plus 1. Now I can just change row 3 with row 2 and I'll have a 1 right there. All right, so I'm going to do, now I've already done this row operation and I didn't want to write a whole new matrix just to change all these signs in row 3. So that's what I did right there. So now I'm just going to do row 2 switched with row 3. Row 2 double arrow row 3 means switch them. And maybe I will, I'll continue one more. I'll squeeze it in here. Row 1 doesn't change. 1, 2, negative 1, negative 1. Now the bottom row 3 is going to become row 2. So 0, 1, 2, 1. And then this old row 2 is going to go down to row 3. 0, negative 3, positive 2, positive 5. Okay, and usually, in case I didn't mention it, I always put a box around the 1 after we create it. We got this 1 right where we needed it to be in row 2. This is the pivot in row 2. So now I'm going to use this to get a 0 below it. So if I were to add 1, well, that wouldn't do it. But if I add 3 times row 1 into this, I'd get a 0 here. So I'm going to do, for a row operation, I'm going to do row 3 plus or minus. It'd be plus 3 row 2 plus 3 times row 2. So row 1, no change. 1, 2, negative 1, negative 1. Row 2, no change. Row 3 plus 3 times row 2. So negative 3 plus 3 times 1. Oops, I ignored the 0. 0 plus 0 is 0. And then negative 3 plus 3 times 1 is 0. 2 plus 3 times 2. 2 plus 6. That's 8. 5 plus 3 times 1. 5 plus 3 times 1 is 5 plus 3, which is 8. Great. Okay, since I am slightly limited on space, I'm going to do the next thing kind of in line without writing an entirely new matrix. What's the next thing I have to do? Well, I got this one, and I got zeros below it. I got this one, I got zeros below it. Then I turn this 8 into a 1. So all I need to do is divide the entire row by 8. So I'm doing 1/8 of row 3. So basically I turned 0088 into 0011 because I divided all 4 of those numbers by 8. Okay, so again, I'm cheating only because I'm running out of room a little bit. So remember, 8 over 8 is just 1. So what does the bottom row tell us? The bottom row tells us that z, 1 times z, is equal to 1. This 8 over 8 is just a 1. 0x plus 0y plus 1z, which is z, equals 1. So z is equal to 1. The second row tells us that y plus 2z is equal to 1. Remember, we've got the x column, the y column, and the z column. So y plus 2z is equal to 1. Y plus 2 times z, but z is 1, is equal to 1. So that's an arrow. Y plus 2 equals 1 means if you subtract 2 from both sides, you get y equals negative 1. So I'm going to put a box around the z and the y. And now we've got to go up to x. This says x plus 2y minus z equals negative 1. We have x plus 2 times y, because y is negative 1, minus 1 times z, minus 1 times 1, equals negative 1. Make sure I got that correct. 1x plus 2 times y minus 1 times z equals negative 1. So that would be like x, that's a minus 2 and that's a minus 1. Negative 2 and a minus 1 is negative 3 equals negative 1. Add 3 to both sides and we get x equals 2. All right, so the solution is written as an ordered triple. XYZ would be 2, comma, Y is a -1, and Z is a 1. This is the solution. And I'm going to make one quick statement, since I don't think I discussed this earlier. An equation like this, where you have 3 variables equal to a number, with coefficients in front of them, each one of these represents a plane in 3 space. For example, you could think of it as this being a wall, and this being an adjacent wall to it. So they meet at a line, and then this could be the floor. And the corner of the floor where these 2 walls meet would be this solution. So if you've got 3 planes like this, they meet at a single point. And this would be the XYZ position in 3 space of that point.